Hey everyone, it's Dr. Walker. This is video 61C called angular momentum. Let's look at calculating the angular momentum of a particle. As you can imagine, the angular momentum is just a rotational equivalent of the linear momentum of a particle. So let's see how we can derive this expression. Let's consider a particle right here. It has a mass m, it has a position vector r. Let's say that there's a force acting on it. Let's say it's acting on it to the right. There's a net force on it, and it's causing it to have a velocity and thus a momentum, a linear momentum, going to the right. How do we find a torque on this particle if this force is causing a rotation about this pivot point here at the origin? Well, the torque is a cross product of the position vector and the force. So we can write that down. And then we can use Newton's second law to write the sum of the forces as a derivative of the momentum with respect to time. We can use the product rule. I'll spare you all the details, but it allows us to put this r vector inside the derivative. It's kind of a backwards use of the product rule. So now we have the net torque is a derivative of the cross product of r and p, the derivative with respect to t. What we're going to do now is we're going to call this quantity here, we're going to call it L. So that means that the net torque on the particle about the origin is a derivative of L with respect to t. Does this equation look familiar? Hopefully it does. It looks a little bit like Newton's second law. The sum of the forces is a derivative of the momentum with respect to time. So this expression right here is the rotational equivalent of Newton's second law. The forces get replaced with torque, and P gets replaced with L. So what do you think L is? Well, P is the linear momentum, so L, we're going to define it and call it the angular momentum. We've defined the angular momentum L as r cross p. So it is a vector just like the linear momentum. If we look over here at our drawing again, if you take the cross product of r cross p, you put your fingers in the direction of r, you fold them in the direction of p, your thumb should point upward along the z-axis. That's the direction of L. The units for the angular momentum is kilograms times meters squared per second. That just comes from r, which is meters, and p, which is mass times velocity, kilograms times meters per second. So we are going to use Newton's second law here, the rotational equivalent, in a similar way that we used Newton's second law for linear motion. We also, if you remember, we wrote it as the sum of forces equals ma. We use Newton's second law to find the acceleration of objects. Now we can use Newton's second law to find the angular acceleration of objects. Remember, Newton's second law was also given as I alpha. So we can use it to find the angular acceleration of objects. We'll do an example soon. Then we can use this expression to find the angular momentum of a particle. Let's look at a question here. We have an object of mass m. It's located at a horizontal distance r from the origin, so it's located right here. It's moving in a horizontal straight line with a speed v. So if it has a speed v, a velocity this way, that means it also has a linear momentum in the same direction as the velocity, because we know that linear momentum is mass times velocity. What is the magnitude of its angular momentum about the origin? We already know its direction by using the cross product, because angular momentum is r cross p. We just learned this. Put your fingers in the direction of r, use your right hand. Fingers in the direction of r, fold in the direction of v, thumb should point up. So now we're looking for the magnitude of this momentum. Take a second, see if you can figure it out. It turns out in this example, and it may not have been really clear, but the v is perpendicular to the r. This is a special case, and you should definitely take a note of it. Special case when v is perpendicular to r. Let's go ahead and use our definition of the angular momentum. Rp sine theta. Theta is the angle between r and p, which is 90. Sine of 90 is 1. So it is the angular momentum, just looking at the magnitude here, it's Rp, P is mv. So there we have it. Whenever the velocity is perpendicular to r, then the angular momentum is going to be mvr. So we're going to use this result pretty regularly to find the magnitude of the angular momentum when v is perpendicular to r. Okay, so what about if it's not just a particle that is rotating? What if it's a whole object, right? Or a whole rigid object? How do we find the angular momentum of that whole object? We can take the same approach that we did when we found the kinetic energy of a whole object. Do you remember what we did? We split up the object into a bunch of little masses. We looked at one mass. So if we just look at one mass here that makes up this rotating object, we can find the angular momentum of this particle using the definition that we just learned. The angular momentum of that one particle of mass mi is just r cross p. Because they're perpendicular, r and v are perpendicular, it's mrv. And then we can use the definition v is r omega to plug in our omega here and have two r's. That's the momentum, the angular momentum of one particle. And then we just want to sum up all of these to get the angular momentum of the whole entire object. So we do a summation. And hopefully you recognize the sum of mi squared, that's our moment of inertia. So that gives us this expression for the angular momentum of a rotating object, it's I omega. Hopefully it looks familiar. The linear momentum of an object is mv. So P is replaced by L, M is replaced by I, and V is replaced by omega. The regular conversions that we are used to. The unit for angular momentum is the same for a particle or for a rigid object.